Today we are going to discuss about the introduction to noise. Earlier we have studied about the random process and even random variables in the earlier units and spectral densities, power spectral density. So uh, while in a communication channel, when we are passing a message or transmitting a message, we may receive some noise or the disturbances. So that disturbance is nothing but the noise which creates or which always interrupts the messages in a channel. So let us discuss more about this noise in this chapter or unit, that is introduction to noise. What is noise? Noise is nothing but an unwanted signal which interferes with the original message signal and corrupts the parameter of the message signal. This alteration in the communication process leads the message getting altered. It is most likely to be entered at the channel or the receiver. Common example of this is in a radio receiver's his sound or buzz sound in telecommunication conversation, or a flicker noise in the receivers at the TV or television. Usually it changes with the time, whether it is analog or digital, but the noise is created at the receiver side, creating the disturbances for the message which has been transferred. So, what are the main effects of the noise? So, usually it affects the desired pulses, may be cancelled in a communication. So, noise produced unwanted pulses or may cancel desired pulses in pulse communication. So, it may also cause series errors in the computational process, which are mathematical errors. And it also limits the range of the system for a given transmitted power. And it also affects the sensitivity of receivers and may reduce the bandwidth of the system. So, to avoid these, we need to take care while transmitting the signal. For a communication channel, noise is the main thing to be avoided. So different types of noises are there. There are two types of noises created in the communication channel or the system while transferring the messages. So usually externals through the external source and as well as through the internal source. So external source, this noise is produced by the external source, which may occur in the medium or a channel of communication, which cannot be completely eliminated. The best way is to avoid the noise from affecting the signal is external noise are usually with solar noise and cosmic noise and industrial noises. Example for the external source of noise. And for internal source, this noise is produced by the receiver components while functioning. The components in the circuits, due to continuous functioning, may produce few types of noises. This noise is quantifiable. A proper receiver design may lower the effect of this internal noise. Most common example of this type of noise are thermal hesitation noise, or electrical noise, short noise, transit time noise. Miscellaneous noise is another type of noise which includes flicker, resistance effect, and mixer generated noise, etc. So, in external noise source, atmospheric noise or static is caused by lighting discharges in thunderstorms and other natural electrical disturbances occurring in the atmosphere. These electrical impulses are random in nature, hence the energy is spread over the complete frequency spectrum used for radio communication. So in this extraterrestrial noise, so it is the noise through solar. This is the electrical noise emanating from the sun. Under quiet conditions, there is a steady radiation of noise from the sun. This results because sun is a large body at a very high temperature exceeding 6000 degrees on the surface and radiates electrical energy in the form of noise over a very wide frequency spectrum, including the spectrum used for radio communication. The intensity produced by the sun varies with time. In fact, the sun has a repeating 11-year noise cycle. During the peak of the cycle, the sun produces some amount of noise that causes tremendous radio signal interference, making many frequencies unusable for communication. So, in in general, in industrial, noise is the disturbance created through man-made noise. It is meant the electrical noise produced by such sources as automobiles and aircraft ignition, electrical motors and switch gates, leakage from high voltage lines, fluorescent lights, and numerous other heavy electrical machines. Such noises are produced by the arc discharge taking place during operation of these messages. Such man-made noise is most intensive in industrial and densely populated areas. Man-made noise in such areas far exceeds over all other sources of noise. So, industrial noise source such as electrical disturbances in industries, automobile and aircraft ignition sparks from electric motors and switching equipment, leakage from high voltage lines across talk between channels are industrial noise. Flicker noise. At low audio frequencies, noise called flicker noise is formed in transistor. It is proportional to the emitter current and junction temperature and inversely proportional to frequency. It is ignored at 500 Hz, usually seen in CRO screens and TV screens. Thermal noise. Noise power is also proportional to the bandwidth over which it is measured. That is, P is directly proportional to temperature and P is directly proportional to bandwidth, which is given as P is equal to KTB, where P is equal to maximum noise power output of a resistor, K is Boltzmann constant, and T is absolute temperature, B is bandwidth over which noise is measured. The power density spectrum of noise voltage contributing to the thermal noise is given by S of omega is equal to 2 kTb by 1 plus omega by alpha whole square. So it is the power density spectrum of thermal noise. Graphically, it is represented with omega on the x-axis and S of omega, that is power, on the y-axis. It is usually lies from low frequencies to high frequencies uniquely. So the number of free electrons in a conductor are very large. Practically, power spectral density is independent of frequency. That is S of omega is equal to 2 KTB, KTG. So equivalent noise temperature. It is defined as the noise temperature with respect to the available noise power or power spectral density for a passive RLC network. The noise temperature is given by T is equal to P by KB Kelvin. This temperature is called equivalent or effective noise temperature. Equivalent noise temperature depends on power spectral density of noise. So thermal noise is often referred to as a white noise because it has a uniform spectral density. So this thermal noise power spectral density, it is denoted uniform noise spectral density, and its equivalent circuit is shown, that is resistor and ideal noiseless source with voltage source. Short noise. Short noise was originally used to describe noise due to random fluctuations in electron emissions from cathodes in vacuum tubes, called short noise by analogy with lead shot. Short noise also occurs in semiconductors due to the liberation of charge carriers. For a PN junction, the mean square short noise currents is IN square is equal to 2 of IDC plus 2 I naught into B, where I is the direct current as the PN junction as saturation currents. I naught is the electron charge and B is the effective bandwidth. So noise through two-port network, it is denoted like this. Consider a two-port network with input spectral density S of omega and output spectral density S naught of omega with network transfer function H of omega. When the message is passed through the two-port network, the noise available at the output is contributed by input noise and the noise generated internally by the system. Since the resistors and active devices in two-port networks acts as the independent noise sources, the signal quality degrades at the output. The signal which is corrupted by the noise at the output can be measured in terms of signal to noise ratio and noise figure, equivalent noise temperature, etc. The output noise spectral density is given as S naught of omega is equal to S of omega by H of omega whole square. Output noise is equal to noise power is P is equal to 1 by 2 pi integral minus infinity to infinity over the interval minus infinity to infinity S of omega d omega. And the RMS noise voltage is given as Vn is equal to 1 by 2 pi over the interval minus infinity to infinity S of omega d omega whole to the power of 1 by 2. So signal to noise ratio. The ratio of signal to the accompanying noise power is called signal to noise ratio. It is given by S by N is equal to Vs square by Vn square. That is signal power and noise power. So available power gain is given by maximum maximum power spectral density of the signal at the output by maximum PSD of the signal at the input. It is given by G of omega is equal to S of omega at output side by S of omega at the input. So available power gain is given, and equivalent noise bandwidth is nothing but W by 2 pi hertz. W by 2 pi hertz. B is equal to W by 2 pi hertz. In the context of the noise, this is the material regarding the noise, the effects of noise. So noise may cause serious problems. Classification of noise is external noise and internal noise. In external noise, it is atmospheric noise, industrial noise, internal noise, transit time noise, flicker noise, thermal noise, or resistor noise, equivalent noise temperature, power gain. Just now I have discussed noise in cascade amplifiers, antenna noise,